This is lecture 20 on section 11.1 on sequences. So in chapter 11, so keep in mind we're skipping chapters 9 and 10. Chapter 9 is on differential equations, and that we have an entire course on that. So unless we have extra time at the end of the semester, which I don't anticipate, we won't get to anything in chapter 9. In chapter 10, we might circle around after chapter 11 and pick up a couple of sections, just depends on how quickly we get through. So chapter 11 is all about the idea of sequences and series. So very different from the integration that we're doing. So we're kind of changing totally the direction we're going here. So the first thing you need to know is that a sequence is a list of numbers written in a definite order, okay? So you have an A1, A2, A3, A4. So something that you can enumerate where this is the first one, this is the second one, this is the third one, this is the fourth one, okay? We use the subscript notation, the 1, 2, 3, 4, to note its position in the order, right? Note that I'm starting here at n equals 1 as our first term. Some people start them at n equals 0. For example, in my biocalc class, that book starts them at 0, so that's what we do. But typically in the Stewart calculus book that we're using, our sequences start at 1. Okay, so you start counting at the natural numbers 1. And so A sub n represents a sequence, and we use the A letters, A, B, C, D, whatever it is, to name your sequence. So AN is A1, comma, A2, comma, A3. They're not being added. It's just a list of numbers that goes on infinitely. Okay. So if we're going to write the first 5 terms of the sequence, all you're doing in order to find each term is to plug in n equals 1, then n equals 2, then n equals 3. So for this first one, you have an equals, when you plug in 1 over 1 plus 1 is 1/2. When you plug in 2 over 3, and then 3 over 4, and then you can start to see the pattern and move a little quicker, 4 over 5, and 5 over 6, right? And they go on forever in that way. Okay, some other sequences that are common that pop up, you get -1 to the n. -1 to the n is the sequence that allows things to alternate, right? Because when n is an odd number, then you get -1 an odd number of times, which means your value is -1. But if n is even, you have an even number of -1s, and they cancel each other out to be a positive one. So starting with your first one being negative, they're going to alternate back and forth. The thing on the bottom here, the n factorial, the n exclamation point, that's n factorial. And what it means is these are, for whatever position you're in, it's that number times all the numbers smaller than it down to 1. So, for example, 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. Okay. And so the sequence n factorial, 0 factorial is 1, but we're starting at 1. So 1 factorial is 1. 2 factorial is 2 times 1, which is 2. 3 factorial, which would be 3 times 2 times 1. That's 6. 4 factorial takes the 6 and multiplying it by 4 gives us 24. 24 times 5 gives you 120, and 120 times 6 gives you 720, and you can see how it grows pretty quickly. Anytime you see this pattern of 6, 24, 120, 720, you know you're talking about factorials. Okay, so that way, when I'm finding my first 5 values, what we're doing here, this is an equals, you're taking -1 to the 1 plus 1 over 1 factorial. So that's going to be -1 to the 1 is negative. 1 plus 1 is 2, so that's -2 on top. And 1 factorial is just 1. In the second position, you have -1 squared, 2 plus 1 over 2 factorial. So -1 squared will be positive, so this value is going to be positive. 2 plus 1 is 3. And 2 factorial is 2 times 1, which is 2. And I'll write out one more, and then we kind of get the pattern here. So -1 cubed times 3 plus 1 all over 3 factorial. So our third position, negative 1 cubed, is negative. 3 plus 1 is 4, so negative 4 on top. 3 factorial is 3 times 2 times 1, so that's 6. Then we want the fourth term. So negative 1 to the 4 would be a positive 1. 4 plus 1 would be 5. And 4 factorial is 4 times 3 times 2 times 1, which is 24. And our last one, number 5, negative 1 to the 5th would be negative. 5 plus 1 is 6. And 5 factorial is 120. You're taking the 5 times 4 times 3 times 2 times 1. Okay, so those are the first 5 in that sequence. Number 3 is not nearly as complicated. We're going to start with 1, so that's the square root of negative 2, which doesn't exist, but hey, there it is. Square root of, when you plug in 2, that's going to be negative 1. Then we get 0 when you plug in 3. When you plug in 4, you get square root of 1, which was 1. And when you plug in 5, you get the square root of 2. Okay, so that's going one direction. If I give you the general form of the sequence, you need to be able to write out terms. Then, if I give you a sequence, I want you to be able to find the general form. So with this one, what is our AN? For number 1, the first thing I notice is that every other term is negative. So we're going to have a negative 1 to the n. But notice that my first one is negative. So if I leave it as n and I start my sequence at 1, negative 1 to the first makes it negative. So what I have to do is I have to add 1 so that it moves it to the even terms, the second, fourth, sixth, etc. term. So that's how I get my negatives. And then I'm looking at the numbers 1, 4, 9, 16, and 25, and those are perfect squares. So that is n squared. So that is my sequence there, negative 1 to the n plus 1 times n squared. Number 3. Okay, so one of the things I want to be careful about here is that sometimes our sequences are simplified, and so we can't always see what's going on. So I want to see if I can figure out what denominator these things should have had. So I see a 4 and a 2, and this 1 ended up canceling out. So I think these should probably all be over 4. Let's see if we can recreate something that we can find patterns with. So the 3 over 4 stays. In order to make 1, this would have to be 4 over 4. 5 over 4 stays. Get common denominators for 3 halves. That would be 6 over 4. Then you have 7 over 4. 2 would be 8 over 4. Then you have 9 over 4. And 5 over 2 would be 10 over 4. And that looks like a sequence I can work with. So notice that the denominator is 4 for every single one of them. And then I'm starting at 3 and jumping by 1. So here's like a little side note. So if you have, and I don't want to use A. Let's use P times N plus Q, right? If this were your sequence, then you would, when you plugged in 1, you would start at P plus Q. And then each time you're adding an extra P. And that may not make a lot of sense, but if we do some examples, you'll catch on pretty quickly to what this is. So if I make this 3n plus 4 and you plug in 1, I start at 7. And then I add another 3. So when I plug in 2, that'd be 6 plus 4 is 10. 9 plus 14 is 9 plus 4 is 13. And then you would get 16. And see what's happening. I'm adding 3 each time. And that adding of 3 is what this 3 represents. And then this number is always, if I backed up one more and went to 0, would be the number that you start with here. So you can think of it as, how do I find that one? Well, that's this number subtracted by how I'm changing. So that may be a little bit complicated, but here's how we figure it out. So in this case, in the numerator, they're each adding 1 each time. Okay, so then what number do I need to add to 1 to start at 3? Well, I would need to add a 2, so I make it 2n. Okay, and you can check to see that if you picked the fourth term, when you plug in 4, you do in fact, sorry, I lied. The other way around. I'm jumping by 1. So a 1 goes in front of the n. And what number do I need to add to start at 2? I would need to to get 3, I would need to have a 2 there. So that when I plugged in 1, I would get 3 over 4. And that way we can check it so that if we check the fourth number, 4 plus 2 is 6 over 4. And that does in fact give us the fourth number. Okay, so that's kind of how linear terms work. All right. Now, this one, I'm going to convert that 1 to be a 1 over 1. So 1 over 1, 3 over 2, 5 over 6, 7 over 24, 9 over 120, and 11 over 720. So the first thing I'm going to notice is the denominators. Okay, those are my factorials. Anytime I see 624, 120, 720, this one starts at 1. So that means my bottom is n factorial. The numerators are jumping by 2 each time. So I'm going to have 2n. And in order to start at 1, I need this to be, if I plugged in 1, I'd get 2. So to get 1, I'd have to subtract 1. That way, if you plug in 1, you get 2 minus 1 is 1. If you plug in 4, you get 8 minus 1 is 7, which is what gives you this fourth term. Okay, so I just got to test 1. So that's my answer to number 3. Number 4, again, this is 1 over 1, negative 1 over 3, 1 over 9, negative 1 over 27, 1 over 81. So notice that your numerator bounces back and forth between 1 and negative 1. So that's going to give me a negative 1 to the n, but it's on the even terms, number 2, 4, 6. So that means I've got to add 1. Okay, that way, when you plug in 1, 1 plus 1 is 2, negative 1 squared gives you the positive that starts with. And on the bottom, I have powers of 3. Now, if I had 3 to the n, that would start me at 3, then 9, then 27. So I've got to back it up. I want n minus 1. So that when I plug in 1, 1 minus 1 is 0. 3 to the 0 gives me that first term. So that's what I want here. Okay, now, once we've been able to do that, next thing we want to talk about is when a sequence converges. So the most important thing about sequences and series when we get to them is, do these things converge, right? Do they go off to infinity, or as you go towards infinity, do they approach a specific value? And the idea here is that a sequence has a limit the same way a function does, okay? And if that limit exists, if we can get a value, oh shoot, mistypo here, this should be as n goes to infinity. We can make the terms n as close to L as we like by taking sufficiently large n. So if I take really big numbers for n, I can get my sequence to approach a specific value. Okay. If this limit exists and it's a number, we say that the sequence converges. But if the limit does not exist or is positive or negative infinity, then the sequence diverges. Okay, so the only thing good here is if you get a single number. All right, so how do we determine whether a sequence converges? We take the limit the same way we did before. The only difference is that instead of it being a continuous function, now we're really only worried about the natural numbers, 1, 2, 3, 4. Okay, but it works the same way. You can treat it like a function, and it works the same way. Okay, so take a look at this. Let's see, do these functions converge or diverge? So we're going from 5 to 2 to 9 to 6 to 13 to 10. I don't know about you, but this doesn't seem to have a pattern to it. Right? We go 5, then 2, then 9, then 6, then 13, then 10. Nothing that I can come up with. If we look at differences here, this is plus 3. This is plus 7. Plus 3. Plus 7. Plus 3. Plus 7. So, oh no, lied. Minus 3. Hold on. This is minus 3. minus 3, minus 3. Okay, so let's see if we can split this up and see if we can kind of add two things together. So let's make this 5 plus 9, or 5, 9, 13. And then down here, yeah, that's not going to work for us. So I don't think this is going to converge anywhere, right? Because you're going to subtract 3 and then add 7. So for every 2, you have a net add of 4. So you're going to be adding 4 every second term. So if I think about, instead of thinking about 5, 2, 9, 6, 13, let me think about going from 5 to 9, 9 to 13, 13 to what would be 17, right? So really, if we think about the every other one is going to be jumping by 4, starting at 5. So that means you're doing something that looks like 4n plus 1 for the alternate ones. And so that one, in that case, if you take the limit as n goes to infinity of 4n plus 1, that's going to take you to infinity. And so this one's going to diverge. Okay, typically things without denominators that are increasing are not going to converge. Okay, so this one's going to diverge. The second one, 1/2, 1/3, 1/4, your an here is 1 over n plus 1, right? The ones are all the same. On the bottom, you start at 2 and jump by 1. So I have n plus 1. Then if you take the limit as n goes to infinity of 1 over n plus 1, that's 1 over infinity, which turns out to be 0. So this one converges. Number 3. Oh, this one looks tricky. Okay, what's going to happen here? You're taking the limit as n goes to infinity of n factorial over 2 to the n. That's tricky. So that's the limit as n goes to infinity of something that looks like 2 to the n over n times n minus 1 times n minus 2, right? So let's think about a term and what might happen here. So if you think about something large, right? So for an large, if you had 10 factorial over 2 to the 10, right? That's going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And underneath that, I get 10 2s. So I get a 2 underneath each of these. And if I think about them like this, at each pairing, then notice that each of these, except for the last one, each of these are at least 1. So you're multiplying by large numbers over and over and over again. There is no way that this is going to be able to converge to some particular value, because if I add the next number, I'd add an 11 on top with a 2 on the bottom, and I'm multiplying by 5.5. And so that's going to get larger and larger each time. So that's going to go to infinity, and it's going to diverge. Okay. Number 4, we can take the limit here, as our an is written out, of 3n to the 6th over 2n to the 6th plus n cubed plus 2. And this is going to follow our limit laws. So normally when we plug in infinity, this would be infinity over infinity, but we're looking at the powers. And when you look at the powers and they're equal, so we have a degree 6 over a degree 6, we just get the coefficients of the leading term. So you get 3 halves, and so this one converges. Okay, now what's next? We want to decide whether these sequences converge or diverge. Okay, now notice that these are all a number with an n power. So what happens with 3 to the n? So as n gets large, 3 to the infinity You're taking 3 to a ridiculously large number. That's going to be infinite, right? That's 3n times. So this one will diverge. What about negative 3, right? Well, if you have negative 3 to the n, that series, so this is the same as, so let's look at this. Let's look at the limit as n goes to infinity of negative 3 to the n, and let's separate it. I can make that negative 1 to the n times 3 to the n. And we know that this one bounces back and forth from 1 to negative 1, so that's not going to approach a particular value. And this one is infinite, so this is going to end up being infinite as well, right? And if you think about the terms in the sequence also will show that you this. So you start out with negative 3, then positive 9, negative 27, positive 81. And you can see what's happening, right? If you separate them, you get a negative 3, a 9, a negative 27, and 81. I don't even know what comes next. A negative 243, right? This one's headed off to negative infinity, while this one is headed off to positive infinity, and those two can't go to the same place. So this is going to end up being a does not exist, right? Anytime you end up with something that is alternating, unless this part is headed to 0, it's not going to converge. Okay, so in that case, we would say that this one diverges. What about 0.1 to the n? Well, if we think about what Cn looks like, this is 0.1, and then 0.1 squared means I'd get 0.01, and then 0.1 cubed would be 0.001, and then 0.1 to the fourth would be 0.0001, so forth and so on. And you can see that that one is going to converge to 0. What about negative, right? So, okay, well, negative 0.1 is your first one. And then you'd get positive 0.01, and then negative 0.001, and then positive 0.0001. And now if you think about splitting the positives and the negatives, negative 0.1, negative 0.001, 0.01, 0.0001, these are both going to 0. So that means that my limit is going to go to 0, and this one is going to converge to 0 as well. Okay, so we can use a little bit of logic about what we know about numbers that are increasing and decreasing. So what we notice here, notice that if you have a number that's bigger than 1, like 3 and negative 3, or it's the negative version, right, those diverge. But when you have 0.1 and negative 0.1, those both converge. So we get this statement. So if your number, your R value, right, that's you're taking powers of, is between negative 1 and 1, then when you take the limit, you get 0. Okay. If R is equal to 1, then you get 1 to the n, which is just 1. So you get 1 all the time, and the limit is always 1. So that converges as well. But if you're greater than 1 or less than or equal to negative 1, then the sequence diverges. And that's because you're getting larger numbers that, that bounce back and forth and become large or equal to 1, and those are going to diverge. Okay, so that's what we know about our exponentials. All right, now I got a quick list here because this is related to limits. We get all the same properties for the limits of sequences that we get for the limits of functions. So these are all of the properties that you should have in your notes from Calc 1 about limits of functions. This just happens to be limits of sequences. So nothing changes here at all. You even get the squeeze theorem back. The other thing you get is that if you look at the limit of the absolute value of an, if that is 0, then your limit is also 0. And we can notice that from our example up here. So notice that both 0.1, right, to the n and negative 0.1 to the n both converge to 0. So if my positive 1 converges to 0, then alternating the signs as you go to 0 does not change it. So you can look at you can also look at the absolute value of something to determine whether it's going to go to 0. Okay. All right, and I promise we're getting there towards the end. We just have a couple more things to do. So I think what I'm going to do is I'm going to go over these 5 problems here, and then I'm going to take a break and put the other half in another video because we're running a little long. So first of all, we want to know if an equals n squared over n plus 2, does this converge or diverge? So we want the limit as n goes to infinity of n squared over n plus 2. Again, you would get infinity over infinity here, but look, you have a higher degree in the numerator than the denominator. And so this is going to go to infinity, so this will diverge. When you have, let's see, the limit as n goes to infinity of the natural log of n over n. This is also infinity over infinity, but we can pull out L'Hopital's rule, and we probably could have done that above as well. This is the limit as n goes to infinity, and you take the derivative 1 over n over 1, and that's 1 over infinity, which is 0, so this one converges. So don't be afraid to use L'Hopital's rule. For -1 to the n, this is just the sequence that goes -1, 1, -1, 1, -1, 1. So there's no way you're going to converge because it's just going to bounce back and forth. So this one diverges. And then lastly, on this one, we can look at the absolute value. We can use that rule that we have above. And that just means I can take away the part that changes the sign. So that's just the limit as n goes to infinity of 1 over n squared. And that's 1 over infinity, which is 0. So this one converges as well. All right, this one gets a little bit tricky. What happens here? So we're going to leave that one for discussion for another day. But essentially what you want to think about is, what are the terms here? So 1 factorial is 1. 1 to the 1 is 1. 2 factorial is 2. And then you get 2 squared, which is 4. The top is going to be 3, and then 3 cubed is 27. The top is going to be 4. The bottom is going to be 4 to the 4th, which we're already getting past my mental abilities. Is 256. So you can see very quickly that the denominator is getting large quickly. So this is going to converge to 0. Okay. So we know that it's getting smaller and smaller and smaller. We're going to stop the video here.